everyone. This is Orion's Brightest Star, and today we are going to be discussing two topics in differential geometry, namely curvature and plane curves. So to begin, we're going to be thinking about curvature. So curvature is denoted usually with a kappa, Greek k, and it is a function from the interval I to some number from 0 upwards to infinity. And what we want this curvature function to capture is we want it to essentially capture how much the curve bends at a given point. And furthermore, we want it to be invariant throughout reparametrization. That is, it should remain the same if we have some reparametrized curvature function, like if we have a curve like that is gamma composed with phi, where phi takes us from a second interval to I, then the resulting function, curvature function, should be, oh, that's not a good kappa, should be invariant. It should be the same. So we're going to construct it from this basic proposition that the curvature is invariant under reparametrization. And we're going to start by examining some of the quantities that we have discussed before. For example, let's calculate velocity. Now, velocity is the derivative of it's the derivative of this, such that we have that. And by the chain rule, we have to take the derivative of the inside function as well. So this is going to be equal to, v of phi of t. So we have this times that. So that's a good start. Let's try to calculate the acceleration of the reparametrization. So now we have to use the product rule. So that's our first term, plus, and then we take the derivative of this one. So we have a v of t, and then chain rule. So our expression is going to look something like this. Now, what if we take the perpendicular part of our acceleration? That is, the component of acceleration that is perpendicular to the velocity. So if we have a velocity v, let's say our acceleration is that, the perpendicular portion would be that, because that is perpendicular to the velocity. So we know that the velocity component would be not present. So this part here is going to be 0. So that's parallel to the velocity, so we can't have that there. However, this term, we can have. We just have to make one small modification. We don't know if the acceleration is perpendicular to the velocity or not. So we say that we're going to put the perpendicular on that. So essentially what we have is the perpendicular component of the acceleration of the reparametrization is equal to phi prime squared times the perpendicular component of the acceleration from our first parametrization of the curve. Now, we see that what happens if we take the norm of the perpendicular component of the acceleration over the norm of v squared. Then we essentially get, I'm going to move this over here, we essentially get phi prime squared over phi prime v squared. And that is equal to, alright, and we can cancel this out, so we get so what we have here is we have a quantity that is invariant under reparametrization, and we can therefore define the curvature function like so. So we have curvature is like that. So now it's time for a proposition. So if we have a curve gamma parametrized by arc length, that means unit speed, then the curvature is simply equal to the norm of the acceleration. So luckily the proof is pretty simple actually. So we learned from the previous video that since gamma is unit speed, then A is orthogonal, that is to say perpendicular, to phi of t. So that means the acceleration is simply just its perpendicular component. And furthermore, we have the curvature equals perpendicular acceleration over velocity squared. But remember that velocity is equal to 1, and this is equal to a of t. So we have a of t over 1 squared, which is simply just a of t. And our proof is done. When we have a unit speed curve, it can be helpful to think of the curve's velocity as some path on a sphere. And what I mean by this is, let's say we have, this time I'm going to use colors. Let's say we have a curve that goes something like this. And let's say we have our velocity is going this way. We can represent the velocity as a mapping onto this onto a sphere. So in this case, we'll be thinking of, let's use red. And our velocity vector will be pointing in the direction that it was pointing in its regular, and because it's unit speed, every velocity is going to, its end is going to be on the sphere because it's unit speed. So that's a nice visualization, and it's something that we should keep in mind as we think about unit speed curves. So now let's define the unit tangent and the unit normal. So the unit tangent is simply just the velocity divided by the norm of the velocity. So it's going to be in the direction of the velocity, but its length is going to be 1. And the unit normal is going to be the perpendicular component of the acceleration divided by the norm of that. So it's in the direction perpendicular to the velocity and the curve, but its length is 1. So let's do an example. Let's create an example. We have a curve. So that's gamma. Our velocity vector is pointing, let's say it's really fast. So this is our velocity. This is going to be our unit tangent. It has length 1. Furthermore, let's say this is the perpendicular component of our acceleration. This is going to be the unit normal over there with length 1. It's not to scale. So that's what we have for the unit tangent and unit normal. So let's take a look at some more propositions. So proposition. If gamma is regular, then for all t and I, we have that the curvature function is equal to the derivative of the unit tangent over norm of the velocity. So remember that since we recall this from a previous video, let me see if I can find the proposition. Yeah, since t has constant speed, since t is unit speed or constant in terms of length, then its derivative is going to be perpendicular to itself. So we have that t prime is perpendicular to t. So the acceleration is the derivative of velocity, which is the norm of the velocity times the unit tangent, the derivative of that. Remember, just multiply this by that and you get what we're looking for. So we got to use the product rule for this. So plus norm of v t prime. So this is perpendicular to the velocity, since it's in the direction of the unit tangent, which is in the direction of the velocity. Similarly, since we already said this is perpendicular to t, this is going to be our perpendicular component for acceleration. So the curvature is perpendicular of acceleration over v squared, which is this v t prime over v squared, and we can cancel that out and we get the norm of t prime over the norm of v. So we also have that the unit normal can be expressed in terms of the tangent and its derivative. So we have that, because remember that this is perpendicular to the velocity, so it's going to be normal to the velocity. Therefore, we have that the derivative of the unit tangent is equal to the magnitude of the derivative of the unit tangent in the direction of the unit normal. And we have established that because the curvature equals this over that, you multiply by that, and we get curvature times magnitude of the velocity in the direction of the normal vector. So, therefore, we can represent the derivative of the tangent as the curvature times norm of the velocity in the direction of the unit normal. So, let's talk about the osculating plane. And what that is it's the span of the unit tangent and the unit normal. So let's talk about what the span is. The span is basically all the vectors that are some linear combination of the unit tangent and the unit normal. So that's that. Let's look at this graphically. So we have a curve here, gamma. Let's say this is our unit tangent, and let's say this is our unit normal. The osculating plane is going to be the plane that looks something like that. And I know that's not really a good drawing, but it essentially contains, and then there's more over here, it essentially contains the tangent and normal vectors, and it's just a plane that contains those two vectors. So you might note, like, if you can really like sort of picture, like, rotate it around in your head, it sort of just like touches the, it's not like directly going through the curve. It's sort of like touching the curve. And more specifically, uh, we define the osculating circle as the circle in the osculating plane with radius so that circle is going to look something like this. So this circle really like is just like kissing the curve. That's where the term osculating comes from, Latin osculare, I believe. I took Latin in high school. I wasn't that good at it, to be honest. I'm much better at math than Latin. But that's sort of like geometrically what's going on with the osculating plane and the osculating circle. So we talked a lot about curvature. Let's talk about a little bit about plane curves. So first, let's consider this rotation from R2 to R2. And what that basically does is, oh, hold on, equals negative yx. So that rotates any vector by 90 degrees counterclockwise. So if we have a vector like that, it becomes something like that. So we can think of the acceleration as, so if the curve is unit speed, then the acceleration is orthogonal to v of t. So we have that the acceleration is some constant times R90 of v of t. So you can think of it as rotating the, so let's draw this. Remember, we're looking at plane curves now. So if we have a curve like this, then, and it's unit speed, it's going to look like this. The green arrow is our velocity, and the blue arrow, we've turned it 90 degrees counterclockwise, and we've multiplied it by a scalar to get our acceleration. Now, note that this scalar can be positive or negative. So let's see what happens if we have a curve that looks like this. And we have that. A 90-degree rotation counterclockwise would give us this. But our acceleration is this, so it has to be multiplied by some negative scalar in this case. So this particular kappa can be either positive or negative. So we call this, which is a function from I to R, we call it signed curvature because it can be positive or negative. So now let's prove that the absolute value is equal to just the regular curvature. So proof, first we have that remember, we're assuming that this is unit speed, so the 90-degree rotation of this velocity is going to be equal to the norm of the velocity as well, and that is equal to 1. So we have that the curvature equals, remember it equals this under unit speed conditions, and the acceleration, as we defined before, of a plane curve, of a unit speed plane curve, is equal to sine curvature times that. And note that this is equal to 1, so therefore the curvature is equal to the absolute value of the sine curvature. Now, I'm not going to derive all this, but you can figure out for yourself that the sine curvature actually has a formula. And if you remember the inner product from 2 videos ago, we're using that now. So this is our formula for sine curvature. And now let's discuss another related concept, which is the angle function. And this exists for plane curves. So it is a function theta from I to r such that under unit speed conditions, we have that the velocity is equal to cosine of theta of t sine of theta of t. So let's take a look at what I'm talking about necessarily. Let's say we have a velocity vector going this way. Its angle function is going to be 0 because cosine of theta, that term should be 1, and sine of theta, that term should be 0. This one is going to be pi over 2, pi, 3 pi over 2, and then when we come back, it's going to be 2 pi. That's sort of what we're dealing with when it comes to the angle function. And note that it can wind up like up to 2 pi, 4 pi, 6 pi. It can also go negatively. Like if we go the opposite way, it could go to negative 2 pi and so on and so forth. Now, one interesting thing about the angle function is that its derivative is equal to the signed curvature. And that just should intuitively make sense because curvature is necessarily about how much the curve is turning. And the derivative of the angle function is also how much the curve is turning. And it's also signed because it can go positively or negatively. So that's the curvature. We can also construct the angle function as an integral from some t0 to t of the sine curvature because of this. You know what? Let's use u. du plus theta 0, which is our first angle. So that basically means if we have like a curve here and we start from here, what is our angle function? Our angle starts at theta 0, and then it keeps accumulating curvature and curvature and curvature, and that should give us our angle, if that makes sense. So the last thing that I'll talk about is a very closely related topic, the rotation index. And the rotation index of a unit speed closed plane curve, so unit speed and closed, is so also it goes from AB to O2. O2 is important, it's not Rn, O2. And it is 1 over 2 pi theta of B minus theta of A, where theta is the angle function as we discussed before. So what does that mean? So if we have a curve that starts here and goes that way, it's going counterclockwise. That has a rotation index of 1 because we have underwent 1 rotation. If we have something like this and it goes like that, that has a rotation index of 2. If we have something like that, actually that's not a good example, hold on, oh, whoops. If we have, there we go, that's a better example. Something that goes like that, that has a rotation index of 0. And if we have something that goes clockwise, like this, that has a rotation index of -1, I'll leave it to you to connect these examples to this formula, but I don't think it should be that bad. But anyways, that's all I have for today, and thank you for listening.